Distribution we're dealing with, W 60, 15 squared, sample size of 30, find the critical value for 5%, one tail because we only want it better than 60. X bar, sample mean, distributed, sigma squared over n over here, that comes down to 7.5. We want to use a Z value of 1.645. That is 1%, sorry, that is one tail at 5%. Memorise that one, 1.645. Positive because we are looking at something getting better. So down here, this is effectively my X minus mu over standard deviation. So my critical value, take away my mean, over the square root of that, set that equal to your 1.645. Rearrange that, you get the critical value of 64.505.
Do you need it to that significant?
To that decimal place,
Yeah.
you mean? I would, well, at least 64.5.
Yeah.
And the next part of the question, part B, says then, a consumer organisation tests these chairs on 30 secretaries and find their sample mean is 67 words. So what do they conclude? That's it.
Doesn't help. What did you say, sorry? 67.
They've seen 67 words after they're sitting on the new chairs. Yeah, that has exceeded this. Our critical value is 64. If it had risen above 64, because it was 60 to start with, if it's got to bigger than there, we would accept things make a difference. So we are concluding now, or we're saying here, if we observed 64.5 or more words a minute, we'll conclude there is an improvement. So because our sample showed that it was now 67 on average, we conclude that the chairs have made a difference.
So that's the second sample, looks like that.
That's not the second sample, that's just looking at a first sample of 30 secretaries sitting on the new chairs. Their sample mean was 67. Historically, we knew the population, we knew that averages were, the mean of the population was 60. So it's now shot up to 67. It's shot up above our critical value.
So the original was 60.
The original was 60.
A new chair, and they do a sample on 30 secretaries.
On the new chair.
They can do 64.5.
No, the sample's been 67. We worked out earlier that if the sample mean exceeded 64.5, we would be accepting H1 effectively. Okay, it's made a difference. Okay, so part C. Now part C says, and you've got part C in front of you, get on screen here in a minute. Part C, if the mean number of words typed in 1 minute is in fact 65, find the probability of a type 2 error. This here is when the great god of statistics is telling you something. That's 65. You think, where's it come from? It's just come from the great god of statistics has now told you that it is 65. So what they're saying there is, for the secretaries actually sitting on the new chair, it's 65. Given that information, find the probability of a type 2 error. Well, what is a type 2 error? Type 2 error is when you accept H0 when it is not true. So what I've got here is it's accepting H0 when H1 is true. Correct. From what we have done so far, look at what's on the screen at the moment. When have we said we would accept H0?
When it's below 64.5.
Yeah, we would accept H0 if the sample mean is below that critical value. So that sentence there, except H0 given H1 is true, becomes the probability that the sample mean is less than our critical value when mu is actually 65. Yes, I can. Okay. So I changed here my H1 being true to H0 being false. If H0 is false, we need then to know what mu actually is. We're told it's 65. That's where that sort of slots in. So this now just turns into, well, working out a probability. It's already less than. So can you work out that probability? You're using, that is your X bar value, that's your mean, you know the standard deviation of X bar. Can you now work out that probability? And you will have then worked out the probability of a type 2 error. I'm going to pause things here, get back to you in a minute.